percent higher flux. So if in the single fired I'm using 10,000, in double fired I can use 15,000. So when I do that, I can shorten the length of my coil because I don't need that much surface area. And as a result, I have two choices. I can keep the same velocity and have lower pressure drop, or I can increase the velocity, fluid mass velocity, and maintain the same pressure drop. It does offer lower residence time, lower coking, and more uniform heating of tubes. So this is some of the features. As you can see over here, typically each pass is almost like a cell over here. So one pass is like cell. And here also the last 5 tubes are put at 3D diameter, and the convection section is on the top in the center. There is one extra feature which has been incorporated in double fired heaters, and that is because each pass has its own radiant cell or radiant section. The designers are able to offer online spalling. So online spalling, what you do is you cut off your feed and inject steam. And when you inject steam, it kind of breaks the carbon coke from the tubes and removes the coke. And we can do that. And once we do that, it will lower the tube metal temperature. So let's say it is a 2-pass heater or 4-pass heater. We go on a reduced load, inject steam in one pass, and then clean it up partially, and then go to the second pass. And if there is a third pass or fourth pass, we do that. Uh, so that is one advantage which is there in double fired, and refiners make use of this facility to spall their heaters, reduce the tube metal temperature by about 100 degrees each time. But after 2 or 3 spalls, they again have to force or clean their fired heaters or coker heaters using pigging. Uh, so the question comes over here, if this heater is so good, what went wrong? Because in the last 5 years, there were 3 or 4 clients who have modern double-fired coker heaters, and they were experiencing only 3 to 4 months run length. So we started studying all the heaters, coker heaters, which we have worked on in the past 25 years. And we made a survey and we found several deficiencies in the double-fired coker heater design. And these things happen when everybody starts building coker heaters. Everybody, all heater companies can offer coker heaters now. And when all companies can offer the coker heaters, it becomes competitive. And once it becomes competitive, vendors start cutting corners and start trying to make heaters more and more compact. And once they do that, you have short run lengths. So if you cut corners, you will get nothing but short run lengths. So but that's what we want to talk about today, is how can we improve the run length. But the reason I'm saying is this has been a problem. We thought double fired heaters will be able to offer 1 year run length or even more, but I think the heaters which we are seeing in the industry are not able to do that. There is a couple of things like in coker heaters, tubes generally last for about 10 years, 8 to 10 years. So every 10 years, you can upgrade your coker heater while retubing the radiant section or retubing the convection section. So you do get a chance to make it right, or at least partially right. And same thing you can do with the burners actually, that if you feel that burners are the ones which are causing problems, you can upgrade them or change them. It is not very expensive, So let us see how cooker heaters are designed. So generally, the designers or the licensors will give you a few guidelines, and sometimes they give you the coil design or the box design, but most of the time they tell you, okay, let us keep the cold oil velocity greater than 6 feet per second. Let us keep the mass velocity around 350 to 400. Keep the flux less than 10,000 for single fired or 13,500 for double fired. And inject boiler feed water or steam, which could be around 1% of the heater feed. So these are some of the guidelines, rough guidelines given by the uh, licensors, you can call it, or the people who are building cooker units. So that's typically what we get. So we did a database of almost 38 cooker heaters we had worked or studied in different times. And most of the cooker heaters are multiple radiant cell horizontal tube box heaters. The flow is from top to bottom. Average inlet temperature is around 600 degrees, outlet is around 930. Inlet pressure about 361, outlet around 70 psig. So it's about 290 pressure drop is the average pressure drop across this heater. Average mass velocity around 400 pounds per second plus foot square. Typical flue gas temperature approach from process coil is around 200 degrees. So, I will tell you a little later the importance of this approach, but to me, it appears very high. And other thing which we noticed was the firebox height to width ratio. Surprisingly, single fired had lower height to width ratio of 1.5 or 1.75, and the double fired were offering 2.02. And some of these heaters have even height to width ratio of 4, because if you put 2 rows of tubes in one firebox, you're basically cutting the width into half. So they even go almost 4 times. So this is the typical analysis of cooker heaters we want to talk about. Uh, what are the different parameters, when we design these things? As I said, fluid mass velocity figures into the coil side parameters, average heat transfer rate, coil size, and pressure drop. These are some of the four. When if you're designing a cooker heater, it will be given to you. And these are all important parameters. Let us start looking at these. Fluid mass velocity is a very important parameter. It is mass flow divided by the flow area of the coils. The units are pounds per second plus foot square. As we said, average is 409. Now, one thing you have to realize is pressure drop is proportional to the square of mass velocity. So if you increase the mass velocity, the pressure drop will go up. Another thing you have to also see is the inside heat transfer coefficient. And inside heat transfer coefficient is important because it controls the film temperature, and film temperature controls the cooking. So inside heat transfer coefficient is proportional to the mass velocity raised to the power 0.8. So you can go for a higher pressure drop, higher mass velocity, and it will give you the low film temperature or higher run length, optimized your run length. The flux, this is the database. The range for single fired started around 8,000 to 13,000, double fired 10,000 to 15,000. And you can see maximum fluxes in double fired are much lower as compared to the single fired. So the third thing before I go to the coking rates, I want to talk about the tube size. And typically in coker heaters, the smaller the tube size, the better off you will be actually. Although you don't want to go lower than 3 inch, because if you have to clean it or remove coke, you will have trouble. So 3 inch is typically the lowest size, but 3.5, or 4 inch is typically the sizes which are used in coker heater designs, and they offer the best surface to volume ratio. You want to have the highest surface to volume ratio so that you can heat the coker feed uniformly. So let's look at the relative coking rates, and this is a chart from Nelson, which he did it in almost like 70 years ago. And you can see there are three parameters plotted over here. There is a fluid mass velocity, relative coking rate, and rate of heat absorption. So you can compare that. Lower the flux, the lower will be the relative coking rate. Higher the mass velocity, the lower will be the relative coking rate. So you can see the importance over here, you know, and how you can optimize your coker heater design or coker heater operation by trying to see if you can optimize or maximize the fluid mass velocity. So let's talk about the fireside parameters. And fireside parameters are heat release per burner, burner to tube distance, burner to burner distance, and burner to air side pressure drop. And these are very important parameters. They determine how long your flame is going to be, how high your flame is going to be, how is the heat distribution in the furnace, how uniform it will be, you know. So these are very important parameters. And the reason I'm talking about these parameters is that these parameters do not affect the design of the coker heater. When you're designing the coker heater, or when you're designing any heater, these parameters do not play any part in the design, and it is left to the designer uh, experience to take care of these. And this is where most of the coker heaters fail actually, and I will show it to you how uh, people work and do it. I think all of you know, fired heaters are designed using correlations designed by Lobo and Evans back in 1940s. And they assumed that there is going to be uniform heat transfer in the firebox, or it's going to be continuously stirred tank reactor model. That is a basic assumption. Now, we have been using these formulas for more than 80 years now, but we also know that these are not true, because today we have the power of CFD modeling, and we can check the radiant section, the burners, we can check the flue gas temperature profiles, we can check the flame length, we can check heat transfer to the tubes and location of hotspots. So what I feel is it is important to do CFD modeling and make sure that, hey, when we designed the heater, we assumed uniform heat transfer in radiant section. Is it true? Are we getting uniform heat transfer? If not, we need to make necessary adjustments in our design to mitigate some of these factors. And you can do that because we have CFD available, and we can ensure that by CFD, we take care of most of these parameters. We also did a survey on the burners. Typical coker heater had about 64 burners. The range was from 3 to 144. Design heat release per burner was about 3 million BTU average. burner to tube spacing about 4 feet or even less than 4 feet, 3.7. The lowest was 2.5 and 6.8, And then comes the burner to burner spacing for uniform heat transfer. We found it was 5 feet burner to burner spacing. That was the average 4.7 feet. So I just want to show you the effect of different parameters and how they play a part in your fired heater run length. So this is a plan view of a double fired coker heater. And if you look at overall on the picture, everything looks all right. The burners are there. There are 3 rows of burners. The center burners are, I think, almost every 4 feet. There are 2 rows of burners on either side, and there is 2 rows of tubes. But this coker heater is having a lot of issues. This heater is having a run length of only about 3 to 4 months. So some of these parameters may be more important. And one of the parameter which I find is important is the burner to tube clearance. And the reason I say is the ultra low NOx burners have very long flame lengths. And when they have long flame lengths, the flames can lean actually. Flame is nothing but gas jet, and it can always lean. These burners flames get affected even by wind velocities. So some of these things could make a great impact. And flames are very, very high temperature gas jets. Typical flame temperature could be anywhere between 2500 to 3000 degrees, So you can see how the burner layout or the heater layout can affect the run length and other parameters, I want to tell you a little bit about the tube metal temperature calculations. We do tube metal temperature calculations at the start of run and at the end of run. This is for one heater, which is a single fired heater. And it was 4.25 inch OD, almost 0.6 inch wall. We assumed quarter inch coke. And we calculated the mass velocity, we calculated the heat transfer coefficient, and then we calculated the maximum flux and the maximum tube metal temperature, assuming a fluid temperature of 950, starts with about 1082 at the start of run with no fouling and almost 1255. Maybe that is the limit of even the coil metallurgy actually. So that's basically the start of run and end of run, Now, if you look at this example and say, hey, I will have 1 degree temperature increase per day, how will that affect? So we plotted this, and if you use 1 degree temperature rise in tube metal temperature per day, 1 degree Fahrenheit, it will take you 87 days to reach EOR or maximum TMT of 1255. So you can see it is not good enough. You don't want 3 months run length of your heater. We are looking at lower temperature rise. If you want 1 year run length, then typically say about half a degree is what you would like to get control, That's how you should control your run length, about half a degree. And that is valid for P9 material where the limiting design temperature is 1300. Please make sure your tubes are designed for 1300 because it requires higher thickness. The other option is, and a lot of refiners have opted for this change, is to upgrade the metallurgy to stainless steel 347. And that gives us about 1500 degrees temperature limit. And there, if you see, we can afford to have a 1 degree temperature rise per day. So I want to show you the coker heater tube skin temperature profile. This is from that same heater where I showed you the burners and tube layout, the plan view. And if you see over here, it's almost 3 months. Within 3 months, it was reaching the design limit of 1200. Here, I think it did little better, maybe about 5 months, but here it did it about 3 months again, and here it did even less than 3 months. So if you see the temperature rise, they had to clean almost every 3 months, 3 or 4 months, which is not acceptable. That requires a lot of effort. You shut down your coker heater for 5 to 7 days. You hire a pigging company to clean it, or you do steam air decoking. You know, so a lot of problems. So the best thing is to minimize coking. So I want to present to you two studies, and this is a double-fired coker heater, and the client was experiencing high tube metal temperatures in the lower tubes. So this is, as you can see, this is 4 cells, a very big coker heater with 8 passes and 4 convection sections and one very large tall stack. That is the configuration. So if you look at the configuration in detail, it was 4 burners. If you see over here, 4 rows of burners, 2 rows of tubes, a central bridge wall in the center. So that was the construction. This heater had 4-inch tubes in the top, 30 tubes, and bottom tubes were 5-inch NPS schedule 160. And this was having a lot of problems actually. And then the client told us they were having maximum coking in these lower 5 tubes. That was, and they were still having high tube metal temperatures somewhere around 2/3 of the height of the box. But these were also coking up very fast actually. So we looked at, we studied it, and we came up with several different revamp options. We said, okay, let us take your four radiant tubes which are at the outlet and change them with 6 4-inch NPS schedule 120 tubes. Now, client wanted to upgrade the radiant and convection coil metallurgy to 347H. So we gave him a lot more options. We told him, hey, if you are retubing it, we would like to see some modifications.